So you'll notice that there's no Chapter 7 YouTube video yet. There will be. This weekend was a bit crazy. And we're actually going to take a couple of weeks to go over Chapter 7. So we're going to introduce some concepts today. And then Wednesday, Thursday, you'll see the Chapter 7 video posted. Your Chapter 7 homework for mastering chemistry is not due for a couple of weeks. So don't worry about that. Deidre, I see your message here. So if you sent me a course message, I have seen it. If it wasn't like burning on fire, I'm sorry I have not responded, but I've seen it and I will respond to you. So just sit tight. And if it's the internet connection thing or anything like that, don't worry. I got you. We'll solve it. So don't worry. So I'm going to catch up on all that today, okay? Promise. You'll hear from me. In my delay, you will not be punished for it. You will not have to deal with the consequences. I will make it right. So don't worry. Also, just want to give you a heads up that midterm grades are due on Friday for me. So I'm going to be uploading those grades like Wednesday, Thursday. So everything that we've done up through exam 2, which you just took over the weekend, will be included. And again, if there were internet connection issues and stuff like that that prevented you from finishing the exam, don't worry. You will have time to finish it. But I'm just giving you the heads up that your grades are going to be updated again this week. So mastering chemistry, everything up through chapter 6. Chapter 7 obviously will not be included. Okay. Is there a hand? Yes.
Are you saying that you're going to combine the courses together, or is it another exam as far?
There is not going to be an exam. No. So we do not have a midterm exam in this course. We have 4 regular exams. We just happen to have one like the week before midterms are due. Okay. So your grade is just going to be everything that's happened up through this past weekend. Okay. You're welcome. So we're starting chapter 7. It's a big chapter. It's on chemical equations, different types of chemical reactions. We're also going to get into stoichiometry, which is doing math with chemical equations. So it's a pretty big chapter. And you're going to need to carry over some of the skills that you learned in chapter 2 with the conversion factors and equalities to this chapter. So just a word to the wise, if that was difficult for you, you're definitely going to want to brush up on the idea of writing equalities and conversion factors and using them to do math. So just telling you straight up, that's what you're going to need. Are there any questions for me before we move into chapter 7 material? We have a lot to cover today, so that's why there's no do now. But are there any questions for me, logistics or anything like that? Speak now or forever hold your peace. All right. Well, if you think of something, you can always throw it in the chat and I'll address it as I can. So like I said, this chapter, we're talking about chemical reactions and we're doing some calculations with those reactions. We're going to start with the equations. I'm going to refresh you on what a chemical change is. And then we're going to talk about the evidence that suggests that you're observing a chemical change. Then we're going to move on to balancing chemical equations. So we talked about physical and chemical changes and physical and chemical properties a few chapters ago. So just to refresh you, since we're talking about chemical reactions, which is absolutely a chemical change, a chemical change occurs when you have a substance that's converted into something else. And there's things that you may observe that let you know that you're observing a chemical change. And we're going to go over those. So you'll want to take notes on this. The types of evidence. The first one you might see, and you don't have to see all of these, but you might see a change in color. So the example that's given here is when iron rusts. It turns into this kind of funky brownish red color. That's a color change, and that indicates that the iron in the nails has rusted. If you have ever lived in a colder state for an extended period of time, or even just driven through, you might see rust on cars. That is a chemical change, and it is quite unfortunate. The second form of evidence you might see is formation of bubbles or gas. If you've ever done the baking soda volcano, where you have vinegar, baking soda, and some soap, like dish soap, that's a chemical reaction. You see the bubbles and it foams up because of the soap. You can also mix calcium carbonate with acid, and you'll see foaming like you do here. So all this foam, those are bubbles. That's forming a gas. The third thing you may see, and again, you don't have to see all of these at once for a chemical reaction to occur. But the third thing you may see is the formation of a solid, which is called a precipitate. You'll need to know that word. So let's say you take two solutions and you mix them together, then all of a sudden you see this yellow solid forming. That is evidence of a chemical change or chemical reaction. The last piece of evidence that can clue you in when you're seeing a chemical reaction occur is that you see a flame, or you have pretty much a change in heat. So the reaction vessel, like a beaker or flask, might get hot or it might get cold. So that change in energy, that change in heat, is evidence of a chemical reaction. Before we move forward, are there any questions about that? That's just the 4 different observations that provide evidence that you're observing a chemical reaction. Are we clear on those? Good. So that was kind of a mixture of review and then kind of cluing you in on ways that you can tell when you're observing a chemical reaction. Now we're going to shift to writing and interpreting chemical equations. So this image here, I don't know if anybody likes to grill or if you just like grilled food in general. I do. I have a charcoal grill in my backyard. Charcoal or bust for me. Love the flavor. Propane is cool, but it's just not the same. The reaction that's happening is you're taking coal, which is just carbon lumped together, and you're burning it in the presence of oxygen gas, which is in the air. And one of the things you're making is carbon dioxide. That's a chemical reaction. So you're taking solid carbon, which is the coal, and then there's oxygen in the air. You're heating it, so you have to start your coal somehow, right? And then you're making a gas. There's different symbols that we use in chemical equations that you're going to need to be able to interpret. And after this, there's a chart that has these in them. So don't worry about trying to write down this slide. Take note of the chart, and that will be more helpful. So to write a chemical equation, we've got a bunch of symbols. The first thing you're going to want to take note of is the arrow. There's an arrow that separates the reactants from the products. The reactants are the ingredients. And the products is just that. It's what you make. It's the result. The reactants are always on the left-hand side, and the products are always on the right-hand side. If you have multiple reactants, they're separated by a plus sign. And if there's heat involved, like the reaction where you've got the coal plus the oxygen, that little triangle that you saw, or maybe you didn't, but there was a triangle, the delta, over that arrow. That means that you need to add in some heat. The last piece that you need to observe with a chemical equation is the physical state that the compounds are in. So in parentheses, you'll always see one of these four to designate the physical state of the compound. So solid, liquid, gas, and aqueous. And aqueous just means dissolved in water. This is the chart I was talking about. So this chart will be more helpful than all the words. So if you want to put this in your notebook, you can print it out at another time, something like that. Are there any questions about these symbols? Alrighty. Now we're going to move on to balancing equations. The first step is learning how to identify whether an equation is balanced or not. In a balanced chemical equation, you have the same number of atoms on both sides of the arrow. So in this picture here, we've got 4 atoms of hydrogen and 2 atoms of oxygen on both sides. That's just a depiction of if I have reactants on one side and products on the other, the number of hydrogens on the reactant side needs to equal the number of hydrogens on the product side. The same for the oxygen. So I'm going to go through this first part. And this is just a practice in identifying how many atoms of each element are on the reactant side and the product side. I'll show you what I mean by that, and then I'll let you try B. So I like to label the reactants and the products sometimes just so that I keep myself straight. And I make a chart. This way I know how many I have on the reactant side and how many I have on the product side. You're going to write down each element that you see. For letter A, we've only got 2 elements, phosphorus and bromine. Notice I didn't write PBr3 because that's not an element, that's a compound. I also didn't write Br2. Yes, this will be posted on Blackboard. All of it will be, okay? No problem, Jordan. So we've got our reactants and our products, and we need to count how many phosphorus atoms we have and how many bromine atoms we have. So on the reactant side, how many phosphorus atoms do you see? Yeah, there's 4. We know this because there's a subscript 4 after the P. What about bromine? How many bromine atoms do you see? So there are 6 bromine liquid. So that means that we've got to take into account the 6, the coefficient, and this 2. So in this compound, there are 2 bromines. So we've got 6 times 2, which equals 12. How about the product side? How many phosphorus atoms do you see? There's 4, because we've got the coefficient out front for 4, and there's no subscript after the P, so we just assume that it's a 1. So that's 4. We do the same thing for the bromine. We've got 4 of these PBr3 molecules multiplied by that subscript 3 that comes right after the bromine. So this is a balanced equation because we have the same number of atoms of each element on both the reactant side and the product side. Do you guys want to do an example, or is this clear enough to you that we can move on? So let me know if you want to try B or move on. Okay, go ahead and try B. I'll give you a minute and then I'll start solving it. So you're doing exactly the same thing. You want to have the number of atoms of each element on both sides. I'm going to start setting up my table. You can keep working. Today we have so much to cover, so you may not always be able to finish the problems that I have you try, but hopefully you'll be able to kind of work through it and see, okay, I understand this, or wait a minute, something's missing. That's what the goal is for doing the practice problems together. You may not necessarily finish it, but you can at least see, okay, I kind of get this. I could probably finish this if I had enough time. Or, I need help. Can you explain it again? Alrighty. So there's my table. For aluminum, pretty simple. There's 2 of them. For iron, we also have 2 because of that subscript. The oxygen, we've got 3. So that's the reactant side. The product side, we've got iron, there's 2. Aluminum, we see the subscript 2 there, so there's 2. And then we see the subscript for the oxygen, there's 3. How'd we do on that? Let me know if you have any questions about it, or else we can move on. We ready to move on, y'all? Okay. I think Blackboard is having a little bit of issue because all of a sudden there were like 4 answers all at once. So, all right. So that same method where we assessed how many atoms are on each side, we're going to use that same process to balance an equation. So I'm going to give you an example, and then we're going to kind of do one together. You always want to check to make sure whether the equation you're supposed to balance is actually balanced or not. Sometimes it's a trick and it's already balanced. We've only got two elements here, aluminum and sulfur. On the reactant side, we've got one of each. On the product side, we've got 2 aluminum atoms and 3 sulfur atoms. Not balanced. The way that we balance an equation is it's called balancing by inspection. So we've assessed the situation. We see where we've got the imbalances, which in this case it's both atoms. So you start by finding the lowest common denominator. Let's start with the aluminum. We've got 1 on the reactant side and 2 on the product side. The lowest common denominator between those two is the number 2. So we're going to multiply everything that has aluminum in it on the reactant side by 2. Until you get comfortable with this, I would encourage you to make a table after each time you make an adjustment so that you see where you are and what still needs to be changed. Since we put that 2 in front, now we've got 2 aluminum atoms on the reactant side. Notice how I didn't make a subscript. Never change the subscript. You only add a number in front of the compound. So we didn't do anything to anything else. But now our aluminum is balanced. Now we've got to deal with the sulfur. What do I need to do to balance my sulfur? Yep, I need to find the lowest common denominator. So that's 3. Now what do I do? I'm going to put a 3 in front of the sulfur. So I'm going to multiply the sulfur by 3. Then I'm going to make another table to double check and make sure that everything is balanced. Now everything is balanced. We've got 2 aluminum atoms on the reactant side and the product side, and 3 sulfur atoms on the reactant side and the product side. And this is a pretty simple example, but it's the same process no matter how many reactants, how many products you have. Now I'm going to help you set this one up, and then I want you to try to balance it. Use the same exact method that we just did. So it says balance the chemical equation when solid iron 2 oxide iron 2 or 3? 3 times 8. No, that doesn't make sense. I think that they may have made a typo here. Either way, you've got this iron oxide compound, and it reacts with hydrogen gas and it produces solid iron and water. We're told the state of matter, so I put that here. It's a solid. Hydrogen gas is one of those diatomic molecules that we talked about in chapter 6. So when you see hydrogen gas, it's H2. And it produces solid iron and water. Yes, question.
Okay, so if it acts on, if it say something like nitrogen gas, would you also put a suffix on it?
Yes. Yes. So this is the equation that you need to balance. I'll give you 2 minutes to get started, and then I'll start setting up my table to start balancing it. So go ahead and get started. And if you get stuck, that's okay. Let me know that you got stuck. So 2 minutes. Good question. And I'll show you how. I'm going to start by doing my chart, as always. So very clearly not a balanced equation. We're going to start, and this is where experience comes in. I'm going to start with my oxygen. But the whole term balancing by inspection, it's really guess and check. That's why I encourage you to do the table after each time you make a change. So we're going to try to balance out this oxygen by putting a 4 in front. So we're looking at this like, oh, that means we're changing the hydrogen too. So that's why the chart is handy, because then we can see what we've changed just by adding the one coefficient. So the answer to your question, how can we change the oxygen without changing the hydrogen? You can't. So that's why if you start with the oxygen, then you can adjust your hydrogen accordingly. So we haven't done anything to the reactant side. So there's still 3 iron, 4 oxygen, and 2 hydrogen. We haven't touched the iron on the product side, but we have absolutely affected the oxygen and the hydrogen. So now we've got 4 times 2 equals 8 hydrogens and 4 oxygens. So the oxygen is balanced, but everything else needs to be fixed. Now let's go for fixing the hydrogen. We've got 2 and 8. Our lowest common denominator here is going to be 8. So we're going to put a 4 in front of the hydrogen gas on the reactant side. Again, we still haven't changed anything with the iron or the oxygen on the product side, but we have changed the hydrogen. Now we've got 4 times 2 is 8. On the reactant side, we've still got the same amount of iron, so that's not balanced. But now we've got 4 oxygens and 8 hydrogens. So now our oxygen and our hydrogen is balanced. Let's deal with the iron. We've got 3 on one side, 1 on the other. We need to add a 3 in front of the iron on the product side. We should be balanced after this. We've got 3 on the reactant side, 4 and 8. Now we've got 3 iron, 4 oxygen, and 8 hydrogens. So now we're balanced. So how many of you were able to get the whole thing, or at least a piece of it? How many folks got stuck? This is useful information. Okay. So for those of you that got stuck, did you get stuck with the hydrogen and oxygen? Was that the sticking point? And if so, let me know if it makes a little more sense now. Okay, good. I will post some balancing equations practice for you and the answer key. The best thing you can do with balancing chemical equations is practice. I'm going to show you another example and walk through that, and then I'll let you balance another one. Yeah, go ahead.
When we're doing, I see it's GS and then I see what looks to be like the cursive L. What are these symbols again?
So that tells you the physical state of matter of the compound. And I use the cursive L just because it really shows that it's an L versus maybe looking like a 1 or something like that. I don't want it to be confused with a subscript, like a number subscript. So that's solid, gas, and liquid. You're welcome. So this question is a little bit more reminiscent of what you might see in your homework or on an exam, where you have to balance the equation and then you choose the one that lists the coefficients in the correct order from reactants to products. So let me go back for a second. So if we had to do that for this one that we just balanced, it would be 1, 4, 3, 4. Anywhere where there's no number written in, it's a 1. So I'm going to kind of get you started for this one. Actually, no, I'm going to let you try it yourself. I'm going to let you try it yourself for 2 minutes, and then I'll jump in the same way that I did before. Because I want you guys to have practice. So practice, take 2 minutes, and then I'll get started. I'm going to get started here. Feel free to put your answer in the chat, and you can keep working while I'm working too. So we've got 3 elements that we need to deal with: iron, oxygen, and carbon. I'm going to start with balancing the oxygen. This one is the most complex. So typically that's a good place to start when you're balancing by inspection. In this case, we're going to have to do some multiplication on both sides. Now that the oxygen is balanced, I'm going to go for the carbon. Now we've got 2 out of the 3 balanced. We'll finally take care of that iron. And then we do our final check, which is very important. Even if you don't make a table after each change that you make, you want to do a final check just to make sure you didn't make any mistakes along the way. Alrighty, so that's balanced. So we've got 2, 3, 4, 3, which is B. I know a couple of you were able to get that. But everybody else, talk to me. Did you get stuck? Did you just need more time? How did this one go? Okay, so more time. Go ahead with your question.
So we started with 2 because, like you said, for are the reactants and products, right?
Yes.
So as far as the reactants, we have F2 and 1. Why do we have F2? We're trying to add the 3 here or something.
No, we're taking note of how many atoms of iron are on the reactant side and the product side. That's what we've been doing. We've been counting the number of atoms on each side and then see where the imbalances are so we can fix them.
Got it. Sorry.
No problem. Yeah, I know that these problems take time. And because you're just, maybe you did it in high school, but it takes some practice to be speedy.
Yes, that was precisely it. I did it in high school, so I was used to it.
Yeah. So if you just felt like you needed a bit more time, that's a good place to be. Unfortunately, time is not on our side for class because we've only got 2.5 hours, which sounds ridiculous. But because of the number of examples that I let you try and do, 2.5 hours can evaporate really quickly. So I apologize if you feel a little bit rushed with the practice problems today, but I at least want you to kind of get started and see where you might get stuck so we can diagnose those issues and then move forward. So are we ready to move forward, or do we need to go through this again? So we're not quite out of the woods yet with balancing equations. There's one thing we have to address, and that's polyatomic ions. Remember from chapter 6 that polyatomic ions are just groups of atoms that share electrons and have an overall charge. When you see a polyatomic ion, you want to make sure that it appears on both sides so that you can treat it as one unit. Here we see the phosphate ion. We also see it on the reactant side. We don't see any phosphorus or oxygen outside of the phosphate ion, so we can actually treat it as one unit. I'll show you what I mean. When you're making your chart, yes,
Will there ever be a time when the polyatomic ions are both required, like on the reactant side or product side?
yes, it can happen. And so oftentimes it will happen with hydroxide, which is OH. You might form water as a product, and there you can't keep it together.
Okay.
I don't, you're welcome. I don't believe that I don't believe you will encounter that necessarily on an exam in this class. But if you take other chemistry courses, you absolutely can. So I just want to make sure that you know what you could see. Okay. So notice I kept the phosphate ion together. So I'm going to count that as a single unit. When I go through and write down how many I have, I will just count how many phosphate ions I have. So I've got 3 sodiums, 1 phosphate ion, 1 magnesium atom, and 2 chlorine atoms on the reactant side. Now we're on the product side. Oops. So we've got 2 phosphate atoms. So kind of looks like a mess over here, right? I promise it's not. It's not that bad. let's start by balancing the polyatomic ion. And if you want, you can kind of try to go through this example along with me. And if you get stuck, you can see how I get through it. But I have another one of these like this for you to balance coming up. So we place a 2 in front of the sodium phosphate compound, which is going to affect the sodium. So now I've got 6 sodium atoms on the reactant side. The product side has not been changed. Next, I'm going to figure out the sodium. We've got 6 on one side and 1 on the other. That always makes it easy. And as you'll notice, I kind of take it one compound at a time. So I'll start with what looks to be the most complex, which is usually when you have something that's 2 things that are non-1 on the reactant side and the product side, like the 3 on one side and 2 on the other. Or I'll start with the polyatomic ions. Then from there, I try to balance out each compound and move along systematically. Oops, did not mean to copy that last one. So because we placed that 6 in front of NaCl, we now have 6 chlorine atoms. And this is why I encourage you to check after each time, because you make changes to other atoms that you need to account for. As you can see, we're going to make a change to the magnesium chloride on the reactant side, and that should take care of both the magnesium and the chlorine. So this is going to be our final check. We added that 3, so now there's 3 magnesiums and 6 chlorines. Whoops. Now we're balanced. So it's the same process, and we had to go through and change almost every coefficient. But if you're systematic and you keep track of what you've changed, you should get the right answer. I want you guys to try one, and then I'll take your questions. So it's the same type of multiple choice deal where you have to choose one that has all of the coefficients in order from reactants to products. Keeping in mind that we have this polyatomic ion here that's sulfate. I'll give you 2 minutes to get started, and then I'll get started. I'm going to get started here. I'll try to limit the narration so you can keep working if you haven't gotten an answer yet. So the first thing I'm balancing is the polyatomic ion. The next thing I'm going to balance is the hydrogen, and that will take care of my sulfuric acid on the reactant side. So we also took care of our hydrogen gas on the product side by balancing out that sulfuric acid. The only thing left to balance is the aluminum. Now we're all balanced. So we've got 2, 3, 1, 3, which is B. So I know a few people were able to get to B. How many people just needed more time? If you felt like you got stuck, let me know where you got stuck. We can't spend a whole lot more time on this, so I want to know. If you have a question, let me know. Otherwise, we can go over it in office hours or something like that. All right? Yeah, so if you're good, the best thing to do is practice. So like I said, I'll post some practice problems for you to balance along with the answer key. Okay. Now we're moving on to the different types of chemical reactions. You see chemical reactions all the time. You experience them in your everyday life. Now you'll have some terminology to actually talk about them. These are all the types that we're going to talk about: combination, decomposition, single replacement, double replacement, and combustion. I'll have a chart at the end of all this that summarizes everything that we're going to go through. The first one we'll talk about is combination reactions. Another word that you may see is called a synthesis reaction. And just to give you the heads up, I abbreviate reaction RXN. So if you see that, that's what that means. In a combination reaction, you're taking two or more elements to form one product. So you're taking simple compounds and combining it into one product. The key here is that you're making one product. Multiple reactants, one product. Decomposition reactions are pretty much the exact opposite of a combination. You have one product that's complex, and it splits apart into I always say product. You have one reactant I literally think every time I have taught this, I make the same verbal mistake and say product instead of reactant. It's like a mind thing. All right. You have one complex reactant, and that splits into two or more simple products. So combination and decomposition, they're the reverse of each other. Single replacement reactions, you have one element taking the place of a different one in another reactant compound. So let's say that you have some zinc metal and you drop it into a flask that has hydrochloric acid in it. And be careful, because hydrochloric acid is a strong acid, very corrosive. You'll start to see some bubbles. Those bubbles are hydrogen gas, because instead of the hydrogen being with the chlorine, it's now the zinc. So you formed a new aqueous substance, zinc chloride, and you've also formed a gas. So the zinc replaced the hydrogen in the acid. That's a single replacement reaction. One element replaces another. Are we good so far? Any questions on these first three types? All right, then let's press forward. And again, the pace is going to be pretty fast because chapter 7 is really big and we need to cover 6 sections today. We're now looking at double replacement reactions. In here, we've got positive ions in 2 different compounds switching places. So we have AB and CD, and we make AD and CB. So we've switched partners here. The other thing you want to take note of is when you switch partners like that, you tend to make something like a solid or a gas that you can observe. So in this first example, you would make silver chloride, which is insoluble in water. So you'd see that precipitate out. In the case of zinc sulfide and hydrochloric acid, you would make hydrogen sulfide gas. And you'd see the bubbles from that. So that's a double replacement reaction. The final type is combustion, which if you drive or if you have been in any kind of motor vehicle, you know what combustion is. Unless you have a Tesla, which is pretty new. It's electric car. But with combustion, you're taking a carbon-containing compound and you're burning it with oxygen to form carbon dioxide and water. So the picture here is burning a candle. That's a combustion reaction. The way that your car makes energy to go is combusting gasoline, which is a carbon-containing compound. So combustion is one of those things that you kind of inherently already know and encounter. You just may not have had the terminology for it. This is the chart that I was talking about that summarizes the types of reactions. I would encourage you to have something like this in your notebook, and it'll help you to recognize the different reaction types. So print it out or recreate it in your notes. So I have a learning check here. I'm going to go through the first one to show you how I identify what kind of reaction I'm seeing. And then I'll let you try the last ones. So here, we've got aluminum and some acid. And I'm noticing that instead of the hydrogen with the sulfate, I now have aluminum with the sulfate. So I've got one element replacing another. That's a single replacement. Yes, I'm still going to post a chapter 7 YouTube video. You're still, because we're not going to finish chapter 7 today. So you'll get that like Wednesday, Thursday. All right. So that's the type of logic you're going to need to be able to identify reactions. I'll give you 2 minutes. Try to classify B, C, and D. And then we'll check in. Let's talk about the rest of these. For B, what did we get? Yeah, this one's a double replacement. And I'll just highlight here that we've got that switch going on. What about C? It's a combination. We're taking simple reactants and making one more complex product. And what is D? It's combustion. So that's identifying and classifying reactions in a nutshell. So if you didn't have any issues with this, then you should be fine. Are there any questions, or can we keep pressing forward? All right. I want to get through this section on oxidation and reduction reactions, and then we'll take a break. I realize that we've been going for almost an hour and a half. Bear with me for one more section, and then we'll take a 5-minute break so you can shake your brain out, okay? So redox reactions, which is what I'm going to call them, you'll hear it referred to that way. So oxidation reduction reactions, the shorthand for that is redox. Anytime you have rust forming, it's a chemical reaction, and to be more specific, it's redox, okay? So we've got transfer of electrons from one substance to another. And redox reactions are really important. We have a lot of them going on in our bodies, and that gives us the energy from food. We've also got a lot of things that use batteries. Redox reactions provide the energy to let all your electronics function. And of course, as we mentioned, rust. That is redox. In a redox reaction, you've got electrons being transferred from one substance to another. And the way that you can remember what's being oxidized and what's being reduced, you can use the oil rig. So oxidation is loss of electrons, that's the oil. Reduction is gain of electrons, rig. Now what I learned was Leo the lion says grr. So lose electrons, oxidize, gain electrons, reduce. Whichever one makes more sense to you, you can use that to help you remember the difference. In either case, whenever you have a redox reaction, you're going to have one thing that loses electrons, which means it's oxidized, and one thing that gains electrons, which means it's reduced. In this example, we've got A here, which has an electron to give. It transfers that electron over to B. So A goes from having this extra electron to not having that extra electron. So it is losing one. So it's oxidized. B ends up with that extra electron. So it is reduced. I'll give you another example. Statue of Liberty is green. Didn't start that way. The copper metal is actually being oxidized, and the color of copper 2 oxide is green. So if we start with copper metal, which you see this 0 here, that means that there's no charge, okay? When you get into electrochemistry, you'll usually see that 0 just to show this is a neutral atom. Copper is a metal, so it's going to lose electrons to form an ion. We already know that. What we didn't know was the name of that, and that's called oxidation. Oxygen gas, which is what reacts with the copper to form copper 2 oxide. Again, we're starting with a neutral molecule of oxygen gas. But oxygen, as we know, it's a non-metal. So when it forms an ion, it's going to gain electrons. That means that it's going to reduce. It is the oxygen molecule, the O2, is being reduced. There's always a pair. If something is oxidized, something else has to be reduced. So are we clear so far on oxidation and reduction? We've got some more examples and we'll do some learning checks. But is this making sense so far? All right, we're going to press on. So like I said before about redox reactions, they're very important in biological systems. And one example is coenzyme FAD. FAD exists in your body, and there are a lot of enzymes that use it to do some really funky complex chemistry and move electrons around. FAD can actually transfer, it can absorb 2 electrons, okay? And you can form what's called FADH2. And in doing so, you can oxidize a molecule like a protein. So redox reactions are very important. You don't necessarily have to know how this particular reaction works, but you should be familiar with the fact that FAD and FADH2 exist and that they're coenzymes that enable proteins in your body to do redox reactions. I'm a biochemist. This is the type of stuff I like. So I could talk about this all day, but I won't. This chart you might find to be very helpful because it summarizes everything we said about oxidation and reduction. And for me, I like summaries. I like to be able to reference something that boils it down to the bare bones. So oxidation always involves loss of electrons. Reduction always involves the gain of electrons. But when we're looking at chemical reactions, we're not necessarily just going to see electrons flowing. So we have to know what it looks like. In a chemical reaction, Oxidation may be the addition of an oxygen. So that example where we had the copper solid, that's addition of oxygen. You might also see it as loss of a hydrogen. So if we had that FADH2 and it goes to FAD or FADH, that's loss of a hydrogen. So those are two ways that you can spot oxidation in a reaction. Reduction, you're looking at loss of oxygen. So if you were to do the reverse with our copper, that copper 2 oxide loses an oxygen to become copper solid. That would be reduction. Gaining a hydrogen would be something like that, with the FAD gaining hydrogens and being reduced to FADH2. So those are some concrete examples of oxidation and reduction. Are we still good? Because I've got some examples coming up, or some practice problems. What I want you to do is identify each of these as an oxidation reaction or reduction. So these are what's called half reactions. It's not the whole thing. It's just what's happening to one of the atoms in whatever compound. So label each as oxidation or reduction. I'll give you a minute and then I'll check back in. Let's get started with A. We have tin solid, and it's going to become tin 4 plus. And we've got these 4 electrons hanging out. In order for tin to become an ion, it's going to lose electrons. When you lose electrons, you're oxidized. So, yeah. So it's that 4E. Those are lost. The other way you can think about it is SN solid, that's 0. To go to 4 plus, that means that you have to lose 4 electrons. Now for B, we've got iron 3 plus, and we're adding an electron. Now we're at iron 2 plus. When you gain an electron, that's reduction. Finally, in C, again, we have electrons on the reactant side. So we're gaining electrons. And that's reduction. Go ahead. Yeah, you had it right the first time. Mm-hmm. Yes. This was by design. I want you to see the pattern. And you saw it. So you get the gold star. So when you have electrons on the product side, that means that you are doing oxidation. When those electrons are on the reactant side, it's reduction. So how do we do on those? Good. Didn't mean to keep going forward before everybody answered, or at least everybody who was gonna answer. So that is, we covered balancing, equations, types of chemical reactions, and then we went over redox reactions and how to identify oxidation and reduction. The next part, 7, 4, 5, and 6, we're going to be doing math with these chemical equations. So this is a good place to take a break. It's going to be short. We're going to take 5 minutes because we need all the time. So get back, we'll say 12:43. It's a weird time, but we'll break until then. Shake your brain out a little bit because we're going to be shifting gears some. So I'll see you back in 5 minutes. All right, everybody, it's 12:43. We're going to get back to it. I know that break was short, but we've got more work to do. So we were balancing equations in the first section of chapter 7. And we're going to go back to those equations over the course of these next few sections. What we're going to do first is introduce the mole. So if you've taken chemistry in high school, you've probably heard about the mole. It's very similar to like a dozen in terms of the context. If you have a dozen eggs, it means you have 12. If you have a mole of a substance, then that tells you information about how many atoms or molecules you have. With Avogadro's number, which is what a mole is, you've got 6.02 times 10 to the 23rd things. It's a really big number. So that could be atoms, or it could be molecules. So an example of atoms would be like carbon atoms. Molecules, maybe water. In either case, if you have 1 mole of carbon atoms or 1 mole of water molecules, you have 6.02 times 10 to the 23rd things. This number can be written as an equality. So if you were here at the very beginning for a lecture, I warned you, equalities and conversions are coming back. I don't lie, not on purpose. Let's put it that way. So when I first went over equalities and conversion factors, I told you, don't forget it because it's going to come back. Here it is. We can take Avogadro's number, 6.02 times 10 to the 23rd, and write it as an equality. 1 mole is equal to 6.02 times 10 to the 23rd particles, which we already said that could be atoms, it could be molecules. And from that conversion factor, from that equality, you can write conversion factors. And the conversion factors are the ones that look like fractions. So you have 1 mole over 6.02 times 10 to the 23rd particles, and you've got the reciprocal. Is everybody with me so far? All we're doing is identifying what a mole is and Avogadro's number. All right. Now, I'm not telling you about this just so we can move on. I'm telling you about it so we can do some math. We can take Avogadro's number and we can convert molecules to moles and moles to molecules. So I'll do this example for you. How many carbon dioxide molecules are in 0.5 moles of CO2? You'll also see me abbreviate mole or moles as MOL. You'll also see it in your textbook. In this problem, we're going from moles to molecules. Whenever you have a problem type like this, you're going to use Avogadro's number. That's our equality, just like from the previous page. If we're trying to go from moles to molecules, what conversion factor am I going to use? To give you a better question to answer, am I going to put the number of molecules on the top or the bottom of the conversion factor? If we're trying to go from moles to molecules. We're going to put it on the top. And on the bottom, we're going to put 1 mole. That's our conversion factor. So we're starting with half a mole of carbon dioxide molecules, or moles, and we're trying to get to how many molecules. Our moles cancel. We're left with our units of molecules, which is exactly what we want. Try putting this into your calculator to refresh yourself on how to use your calculator with exponents. Your answer should be in scientific notation. So don't forget your units. And just like when we were doing the conversions, excuse me, just like when we were doing the conversions in chapter 2, where units were important, units are very important here too. So your answer should be 3.01 times 10 to the 23rd molecules. Also note that sig figs are back. We've got 3 sig figs in 0.500 moles. And Avogadro's number is exact. So our answer needs to have 3 sig figs. Are there any questions on that? If not, you can say you're ready to move on. All right, then let's go. I want you to try this one. Figure out the number of atoms in 2 moles of aluminum. I'll give you a minute, and then I'll write out how to get there. I'm going to start setting up the problem here. You can keep working, though. So this is how you should have set up your problem. You're going to take 2 moles of aluminum and multiply by the conversion factor with Avogadro's number in the top and 1 mole in the bottom. When you do that, your calculator is going to tell you this number. But remember, your calculator does not care about sig figs. We do. Avogadro's number is exact, and in 2.0 moles, we have 2 sig figs. So your answer should be C. It looks like several of you got that. Everybody else talk to me. Are we good with this one? So just to let you know, the math that we're getting into, especially when we pick up with Chapter 7 next week, it's a place that can be difficult. So make sure that when I ask for feedback, if you feel some type of way, please let me know. And if you don't feel comfortable putting it in the chat with everybody, you can send me a private chat message and I'll see that too. Or you can send me a message through course messages, or just come to office hours and get some extra help. But don't get behind just because you feel some type of way about saying that you need help. If you already knew this, you wouldn't be in the class. So it's really okay. Here's one more learning check. I'll give you a minute to try it, and then I'll start writing it out. I'll start setting up the problem. You can keep working, though. So notice in this question, we're asked about the number of moles, not the number of atoms. So your conversion factor needs to be flipped from what we were doing. 1 mole on top and Avogadro's number on the bottom. So you got to make sure to read. And when you do this math, you'll get something like 2.99 moles. but we've only got 2 sig figs here. So your answer should be B. So let me know, is everybody clear on that? Even if you didn't get it, do you understand where you went wrong? Okay. So again, when you're doing your Chapter 7 homework, make sure that you read the problem. And what I typically like to do is write out what it is that I have. In this case, we have atoms. And we're trying to figure out the number of moles. That will help you when it comes to making your conversion factor. So moving on with moles. We can have complex molecules, and those molecules have subscripts that tell us about the composition. When we look at a molecule like aspirin, we can read these subscripts in the context of having one molecule, in which case one molecule of aspirin has 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen. We already know that. But if we were to zoom out and think about 1 mole of aspirin, it's the same concept. You can read the subscripts as moles. So 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen. So the subscripts in a formula tell you the number of moles of each element in 1 mole of compound. In this case, we're talking about aspirin. To give you another example that is kind of more everyday, think about a pie. Let's say an apple pie. If you have 1 pie, that's like the mole, okay? It's one thing that's very complex. In that pie, you may have 12 apples. You might have some flour to make the dough. You might have a couple of cups of sugar because you want it good and sweet. That's exactly like the subscripts. So we've got 1 pie, but if we break that pie up into all its constituents, all the ingredients that are in it, then we've got 12 apples, 3 cups of flour, 2 cups of sugar, whatever. So does that make sense in terms of moles of elements in a chemical compound? So why do we care about that? Okay, kind of. Stick with me, and I hope that it makes a little bit more sense. We can use these subscripts to write conversion factors so we can figure out how much of each element is in a compound. So for 1 mole of aspirin, we can write a conversion factor that talks about how much carbon is in 1 mole of aspirin. We've got the subscript 9 for carbon. That means that we've got 9 moles of carbon for every 1 mole of aspirin. We can write the reciprocal of that. And that would be our pair of conversion factors to talk about carbon. If I were going to write a conversion factor that talks about how much hydrogen, and I wanted to put the number of moles of hydrogen, what would I put here? If you were filling in these numbers, what would it be? The top one would be 8. What would I be putting in the bottom? Exactly. What would my conversion factor be for oxygen? So from the chemical formula, we can write conversion factors. And if you can write this first line, then the reciprocal is the second line here. So you'll need to be able to write these conversion factors by looking at a molecule. We can use those conversion factors to do math. So I'll show you this example. And we are probably not going to get all the way to what I wanted to get through today. So we'll just have to finish it up next week. The question is asking how many atoms of oxygen are in 0.150 mole of aspirin. So we're trying to go from, we have moles of aspirin, and we're trying to get all the way to the number of atoms of oxygen. Seems like a little bit of a stretch, but we can do it. The first part, you're going to have to convert those moles of aspirin to moles of oxygen. And that's using a conversion factor like the ones that we were just writing, where we can figure out how many moles of oxygen are in X number of moles of aspirin. Then the second part is going to be taking those moles and converting it to atoms. That's what we were doing earlier with Avogadro's number. So I'll write this out in two separate colors. The first part of your equation, you're going to take the moles of aspirin and then write a conversion factor that talks about how much oxygen you have in 1 mole of aspirin. We've got 4 moles if we look at the subscript here. That's the first part. If we left our equation here, we would have the number of moles of oxygen. But that's not the question. We need to know atoms. Where am I going to put Avogadro's number? At the top or the bottom? I'm going to put it at the top. Try putting this into your calculator and see what you get. You should get something to where you need to write it in scientific notation. With sig figs, you should get 3.61 times 10 to the 23rd oxygen atoms. So let me know how we're doing. Does this make sense? If I gave you an example to do like this one, do you think you could do it? And don't worry, we're going to do plenty of practice. And we're going to keep doing this next week too. So I want you to try it. Only this time, tell me how many atoms of hydrogen there are. I'll give you a couple of minutes to get a head start on setting up the problem. Setting up the problem is the hardest part. Anyone can just punch numbers into a calculator. But if you don't know what you're doing and what to punch in what order, there's no point. So try to get up to the part of writing an equation, and then I will check in with you. I'm going to start writing it out here, but you can still keep working. We're going to use the same steps as we did before. So that's how you should set up your equation. The first part, we are converting moles of aspirin to moles of hydrogen. Then we're converting those moles of hydrogen to atoms of hydrogen using Avogadro's number. When you do that, with sig figs, oops, not 24. You should get 7.22 times 10 to the 23rd hydrogen atoms. Again, this is going to take practice. So I will put some practice up along with an answer key. There's also a dynamic learning module on mastering chemistry on these topics. So I will put an announcement out with more details because I can't remember specifically what that dynamic learning module is called. But it can help you do some practice and earn some extra credit in mastering chemistry along the way. So that's a great way to make up some points if you missed an assignment or if you didn't do as well on a quiz or homework. You can try to make up some points that way. How are we feeling about this one? And again, I notice who says stuff in the chat and who's still kind of quiet. So for those of you who are quiet, but you're paying attention and going along, make sure that if you're stuck, you let me know. I can't know if you don't tell me. So if you don't feel comfortable doing that, in front of everybody, you can always send me a message privately. If you're still a little confused, that's okay. We're going to pick up with doing this type of stuff next week anyway. But I'll post some practice in the meantime and give you more direction on where you can find some practice on mastering chemistry so you can practice and earn some points. Do you have a specific question about what's confusing you, Deirdre? Okay, so if we can go back to the pie example, you've got one pie. But in that one pie, you have 12 apples, let's say. Well, that's more apples than you have pies, but the apples are a part of the whole. Just like if you have a pizza, one pizza is 8 slices. You've got 8 slices, which is bigger than one, but 8 slices is still equal to one pizza. So 8 moles of hydrogen makes up the bigger part. So if you were to draw like a pie graph, which these parts are going to look terrible, they're not going to be equal. So if we look at a pie graph like that, like a pie chart, this is 1 mole of aspirin. So the whole thing is aspirin. If we break it up into its parts, then we can talk about the different number of moles of each element. So we're really looking at 2 different levels. Okay. So hopefully that helped out other folks who may have been having the same problem. I'm going to take 5 minutes to try to get through molar mass. Not a tough concept, but I'm going to stop in 5 minutes regardless so I can do reminders at the end. Any element on the periodic table, you see that number that's a decimal number underneath the symbol. That's the atomic mass, and it's expressed in atomic mass units. So this is for 1 atom of sodium. If we have 1 mole of sodium, the molar mass of that would be 22.99 grams per mole. This is the concept that we're going to be going over for molar mass. So the molar mass is literally that. It's the mass of 1 mole of an element. And you express the atomic mass that you see on the periodic table in grams. So for carbon, if you were to look that up on the periodic table, you'd see 12.01. Put grams behind it, and now you have the molar mass of carbon. Does that concept make sense to everybody for molar mass? Let's say that we have had something a little bit more complex. We had something with multiple different elements. You can take those multiple elements and add them together. So all of these that you see on the periodic table, you can take all of their masses and add them together. And I'll show you what that means. Let's say we had this compound, lithium carbonate. You would look up lithium, carbon, and oxygen on the periodic table. The molar mass for each of these, you'd write down. And again, that's simply from taking the decimal number that's underneath the symbol and writing it with grams per mole. So that's for each individual element. But we have a compound. And like we just did, these subscripts tell us how many moles we have. So to get the total amount for lithium, we have to do 6.94 grams per mole times 2 moles because we have 2 moles of lithium in the compound lithium carbonate. For carbon, we don't see a subscript here, so we just assume that it's 1 mole. That's what that means. And for oxygen, there's a 3. So we multiply by 3 moles. You do this math to figure out each part. And because of how your book does sig figs, you should separate it out this way. When you multiply 6.94 by 2, when you take into account sig figs, you get 13.8 grams of lithium. So that's how much lithium is in 1 mole of lithium carbonate. You do the same thing for all the others. And then you add them together. That's going to be your molar mass. But we have to take into account sig figs. We can only have up to the ones place. So that's the concept of molar mass in a nutshell. That was kind of fast, but I'm not going to try to press forward and do more. But let me know if that kind of makes sense to you. We'll pick up with this next week. Go ahead. It's because there's only those 2 sig figs and we can get up to the ones place. And we're adding last. So the rules for adding means that we only have up to the ones place, okay? You're welcome. The unit for molar mass is grams per mole. But that's literally it. That's the concept of molar mass. So I had another example here for y'all to do. Obviously, we don't have time for that. But we'll pick up here. We'll do a do now to kind of go back over the using Avogadro's number and the conversion factors, like the problems we were just doing. And we'll do one of these for molar mass. And then we'll keep moving forward. So I'm going to skip ahead. See, we were so close too. But we'll pick up with that next week. Whoa. Hold on here. Let me get to my my end slide. Okay. So, we already talked about midterm grades in the beginning, but for those of you who weren't here right at the beginning, your midterm grades are due on Friday for me. Everything that you've done up through exam 2 is going to be counted towards that grade. So there's no new exam or anything like that. Just know that whatever your grade is, that includes everything up through exam 2, that's what I'm going to be putting in for your midterm grade. So you'll be able to see that in Blackboard like Wednesday, Thursday. You're going to have a chapter check-in due on Sunday, the 18th, just on what we did. Your mastering chemistry for chapter 7 is not due until the 25th. Because we're not going to be finished covering it until next week. Your third exam is going to be, it's going to be available October 28th, so the end of this month. And it's just going to cover chapters 7 and 8. So that's just a heads up if you're trying to figure out your exam schedule and all that stuff. If you have any questions about that, let me know now.